Okay, so we're on page 410 in the chemistry book, and this is a chart of solubilities, and what that means is they're saturated levels. All those numbers there at those temperatures in 100 grams of water, that's the maximum that liquid can hold under those conditions. So they go up. They go from 0 to 100. And you have a lot of different types of compounds. Some of them change drastically and others don't change a lot. The solids will increase in their solubility. All the solids, when you go across and increase the temperature, they all increase in solubility. The gas, they decrease in solubility. So a gas, if you heat up a liquid that's got a gas dissolved in it, you can't dissolve very much. It becomes less and less soluble, that gas, in warmer temperatures. Okay, that's pretty much, it's not common sense, but I think most people can understand. Particles move faster, the gas isn't going to be able to stay dissolved in that situation. Where liquid or solids, they dissolve greater value. Now, you guys can write this down, that's fine, you don't have to. All we're going to do is have you write down your answers to these three questions based upon the table. So look on the table, isolate the compound and temperature, and give me its solubility. Okay? So I'm going to give you a minute or two to do that. So go ahead, look on page 410, table 4, find the solubilities, and then we're going to go ahead and determine what those are. So on page 414, these lines represent saturated levels. Okay, you got all those different color lines on the bottom of page 414. They all represent saturated levels of certain solids. Okay? What I want you to do is I want you to find the point on the line where you have an intersection between 60 grams and 40 degrees Celsius. And then, if it's below that solid line that you're looking at the solid that's dissolving, it's unsaturated. If the point that you find that intersects on the graph is above a line that's saturated level, then that's supersaturated. And if it's right on the line, then that means that solution is saturated. So I have 3 different levels of saturation here, 1, 2, and 3. What you have to do is you have to tell me 1, 2, and 3 if it's saturated, unsaturated, or supersaturated. Okay? So use that graph, okay, in which to find those values. So 80 grams, that would be where it's saturated, right? So we're putting in 60 grams. So is this particular example, number 1, would that be saturated, supersaturated, or unsaturated? If I put 60 grams of LiCl in 100 grams of water at 40 degrees Celsius, would you say that's saturated, unsaturated, or supersaturated? It's unsaturated because it can hold around 80 grams, right? Any questions on that, Emily? So it can hold 80 grams. I'm putting 60 grams in. It can hold 20 more. Make sense? All right. Number 2. We got an answer for number 2. Is that, yeah. Okay. If you go up 70 and you come over across and interpret what that would be, according to that graph, it lines up to be saturated. Does that make sense? You go up from 70, hit the NaNO3 line, which is the blue line, and then you go over, it's right around a little bit above 130. So that's probably saturated. It lines up on the line, the point in which you're graphing, it's saturated. And then the last one, RBCl. You got 120 grams of RBCl. Is that saturated, supersaturated, or unsaturated? Super. What can it normally hold? About how much? at 20? Yeah, between 90 and 100, right? So this is holding 120, so it's kind of like our supersaturated solution. It's holding more than it should hold. Not all substances can do that, though. Okay, good. So when you read it, the first one should hold 80. It holds 60. That's unsaturated. Number 2 is right on the line, which means it's a saturated solution. And number 3 is over that line and would be considered supersaturated. Okay, I'm going to have you put down Henry's law, and then I'm going to show you a demonstration. So Henry's law deals with gases. And we're going to talk about gases and how their solubility changes due to pressure. That's what makes pop taste good. Okay, the idea of putting a liquid under pressure and carbonated pressure, it brings out the flavor of the pop better. It's that effervescence. You can taste that better when it's carbonated. Anybody in here like non-carbonated pops? Anybody? Go to a fountain drink, do you ever get that every once in a while? That non-carbonation is terrible. Terrible. Well, I guess unless you like basically water, sugar, and then the flavoring, because that's what it's going to be if there's no carbonation. So on page 410, we're going to look at that formula, and we're going to use it to calculate. Now, guys, I think most of you can figure this out without plugging it into an equation. Sometimes we think we got to plug everything into an equation in which to get it figured out. And then this one's really easy. I will show the equation, but you don't have to plug it in to an equation if you understand the relationship. It is directly proportional. Okay? So when we look up oxygen, it can dissolve at 20 degrees Celsius, 0.00537 grams. Of O2 per how many grams of water? 100 grams of H2O. That's its solubility. That's how much it can dissolve. Under what condition? 1 atmosphere. If we have it at 1 atmosphere, that's how much it can dissolve. So if you set it up, since it's a directly proportional problem, you put 2.5 atmospheres down here, and you solve for X grams of oxygen. Okay, what are we increasing the pressure by? 2.5 times, right? What's the solubility going to increase by? 2.5 times. It has to be directly proportional. So you can set it up, but if you know 2.5 times greater, you just multiply by 2.5. That's all you have to do. Multiply by 2.5, and you got your answer. Okay? So that's one where we vary the pressure on a gas. We look at it on the table, and on the table it tells us what it is at that temperature. This is room temperature, by the way. 20 degrees is what we say room temperature. That's like 77 degrees. Maybe a little bit warmer than our room temperature most of the time, but that's what they consider room temperature. Okay? So your final answer when you're done is 0.0134 grams. 0.0134 grams per 100 grams of water. Please put per 100 grams of water. Okay? And you do that. The next problem that you have to solve is just as easy. Same idea, proportion. Again, we're using page 410. We're going to vary how much water we're using to dissolve our substance. Okay, so another proportion problem. Okay, another proportion problem that we're going to do. Okay. What is the amount of KNO3 you can dissolve in not 100, but 550 grams? Okay, so again, this is a lot of common sense. You go, oh, I know. If I look on the chart, it tells me 100 grams. So I look on the chart, and it says, hey, I got 61.3 grams I can dissolve of KNO3 if it's placed in 100 grams of water. Now, pressure has no play in solids being dissolved. So, it's really easy, proportion-wise, that's 5.5 times the amount of water. 100 to 550 is 5.5 times. So what I'm doing is I'm increasing the amount of water 5.5 times. So guess how much I can dissolve? 5.5 times more. So you can set it up like that and solve for x. And do your cross multiplication in that. But a lot of times students understand 100 to 550. 100 goes into 550 5.5 times. So that's my multiplier. 5.5. Okay. So that's the other type of question you'd have to do. Okay. And your answer for that one would be 337. 337. So all these are proportion problems. You have to do really easy, using graphs and tables in that. So I'm going to go ahead and give you the worksheet. You guys have the rest of the time. You'll get most of it done before tomorrow. We'll talk about it tomorrow when you bring it in. It's just going to be a completion grade. So if you have it done, you get credit for it. If you don't have it done, then you'll have to show me it later so you can get credit for it. You'll need to use your book, 410 and 414 pages to do it. Okay. Good luck. First couple, you're just looking up the values on the table or the graph. You get down further, there's some problems you got to set up to solve for. Yes, just a second.